Okay, so the purpose of this video is going to be to expand on the introduction of properties of integrals that we did on Friday. And we're just going to take a moment to go through every single one by one and make sure you understand what they mean. We're going to start with order of integration, and I kind of set them up on the second page here. Order of integration we've kind of already covered with our net area because we talked about direction of area. So we have here the integral from a to b of f of x dx equals the opposite of the integral from b to a to b of f of x. Let me give you an example of what this means. Let's pretend that they told us, given the integral from 2 to 5 of some function f of x. You have no idea what that is, but they did tell you that it was equal to -3, let's say. So this is the given. And then you were asked to find the integral from 5 to 2 of f of x dx. And you don't know what the function looks like, never seen it. All you know is that the integral from 2 to 5 is -3. Well, because that's exactly the same function that we're taking the integral of f of x, but instead of going from 2 to 5, we basically switched the order of integration. We went from 5 to 2. Then that's simply going to take the answer, whatever the sign is, and we're just going to multiply it by a negative. And so since it's a -3, the result would be a +3. And that's it. That's what order of integration means. When you change the boundaries, if the function is the same, you simply change the sign of the integral. Okay, all right, let's set up the second one. This is one of my favorites because basically it says that if you take the integral from one boundary to the same boundaries, the answer, no matter what the function is, will always be 0. So let's say, for example, that they ask you to take the integral of -2 to 2 of some function. I don't know, let me make it any function really. Let's do tangent of, and I'm sorry, my boundary should be from -2 to -2. Tangent squared of x divided by 3x minus 1. So that's just kind of a weird function that I made up. Because we're taking the integral from -2 to 2, it doesn't matter how complicated this looks, the result will always simply be 0. Because if you think about it, if we're in a graph situation, if we're at -2 and we never move from -2, no matter what that graph looks like, we've covered no area. Therefore, our answer will be 0. In this one, it talks about taking the integral of a function that has been multiplied by a constant. So let's say that the given is, let's say they tell you that the integral from 0 to 4 of some function is 7. And they ask you to find the integral from, switch the color here, the integral from 0 to 4 of 3f of x. Well, the only thing that differs here is that you are multiplying that function by a constant 3. Because it's a constant, you can really think about it as taking the 3 outside of the integral, and you're left with exactly what was given, which is the integral from 0 to 4 of f of x. We already know that that's 7, so the answer would simply be 3 times 7, which is 21. And you can only do this if the coefficient is a constant. If there is an x here, this property no longer applies because it's no longer a constant, it's now an actual function. Okay? So that was pretty basic. The sum and difference rule is also pretty basic. It just basically says if you're going to add two functions, you can separate those and add the integrals of each to make the total area. Now, what does this mean? Okay, let's say that they tell you the integral from 1 to 5 of f of x dx equals, let's say, 2. And then they tell you that the integral from 1 to 5, notice the boundaries are the same, of g of x is negative 8. And so now, again, you've never seen the functions, you just know this piece of information. They're going to ask you to take the integral from 1 to 5 of f of x plus g of x. Okay, and they're going to do that all under one integral, dx. Well, what this simply means is because you know the integral from 1 to 5 of f and the integral from 1 to 5 of g, if they ask you to take the integral of those two functions added together, we simply take them individually and add their net areas. So in this case, we would have 2 plus negative 8, which of course is negative 6. The same would be true if instead of plus, that would have been a subtraction sign. That's why there's a plus or minus. But instead of adding those net areas, of course, you would be subtracting, which would change it into double negatives, which makes a positive, making this now a 10. So again, if you're adding, you add. If you subtract, you subtract. Key though, you have to have the same boundaries. It doesn't matter if they're different functions, but the boundaries have to be the same. Okay, the additivity is a little more tricky. Let's say that it was given that the integral from negative 3 to 1 of f of x dx was, let's just say 4. And then they told you the integral from 1 to 5 of f of x, again, same function, dx was, let's say negative 10. And they ask you to find the integral from negative 3 all the way to 5 of f of x dx. Well, the first thing you have to make sure is that you are dealing with the same function, and we are f of x, f of x, f of x. But what they are asking you to do is to go from negative 3 all the way to 5. And you basically have been given information in pieces. You know that from negative 3 to 1 is 4, and from 1 to 5 is negative 10. Remember, we're talking about net area here. So what the additivity rule says, if you start at A, which in our case is negative 3, and you go to B, which in this case is 1, and then you start at B, which is 1 again, and go to C, which in this case is 5, that's the same thing as going from negative 3 to 5. And all you have to do is add those net areas. So here we have a 4, and here we have a negative 10. And so, and again, you can kind of see, you go from A to B, B to C, so from A to C gives you the combination of those net areas, which is negative 6. Okay, for the min-max inequality property, it seems really confusing when you first read it, but it's actually kind of obvious. What this says basically is that if you are to find the area using a rectangle with a max and using a rectangle with the min in a function, that your true answer will be somewhere in between those areas. So this left side here, this min times f of b minus a, min f times b minus a, what that means is if you go to the function and find the absolute minimum, which in our example that I drew here is here, and if you multiply that by the width of the interval, what you've essentially created is a rectangle. And that area is going to be less than or equal to the true area. So you can see that that definitely doesn't cover all of the area that we need. Okay? Okay, so if we made a rectangle with a min, that's clearly less than we need it to be. The other option is going to be to make a rectangle with a max. So if you see, this is the highest value of this particular, in the interval of this function. So if we draw a rectangle with that height from A to B, trying to make this a nice rectangle for you, that's supposed to be a B. What you're going to notice if we use the max is that we get something that's way more. So that's going to be greater than or equal to the true answer. The true area is gonna be somewhere in between those two scenarios. You can see this is the true area here. And that's all that's saying, is that if you take the min and make that rectangle, the absolute min, and make that rectangle, that will be less than or equal to the answer. And the answer, the true area, will be less than or equal to, excuse me, if you make a rectangle with the absolute max. And so that's a little bit tricky, but that's basically what that means. The last property is called the domination property, and this one, just like the one before, it's kind of just, when you think about it, it makes sense because of the way it's structured. It says that if f of x is greater than or equal to g of x, so what that means, in the interval a to b, our f function has higher y values than our g function. If that is true, then when you take the area under the curve, that will be higher than the area under the curve of g. So you can see here that if we were to draw the area under the curve for g of x, that's clearly less than the area if we were to find it of f of x, because f of x is larger, and that would be the whole thing here. Okay, so that's what the domination property says. So that's it. That's the properties explained. I'm going to conclude this video. If you want to go ahead and try out the homework that worksheet that you have since kind of the middle of last week, you can go ahead. In the second video, I'm going to make a couple more examples if you need the support. Otherwise, I hope this made sense. Alrighty.